you now have this proposition XS mu measure space F integrable function on X. Given epsilon positive, there exists delta positive such that mu e less than delta implies integral over E mod F d mu is less than epsilon. So there is some kind of continuity condition. In fact, we call this absolute continuity, and which says that if the measure is small, then the indefinite integral of over that corresponding set can also be made small. So proof. Step 1, let F be bounded. So mod F is less than equal to some capital M. Then integral over E mod F d mu is less than equal to m times the integral of d mu over E, which is just a measure of E, and therefore if you take delta E equals epsilon by m, we are okay. So step 2, F not bounded, therefore you take Fn of X equals mod Fx if mod Fx is less than equal to n, and n if mod Fx is greater than n. Then Fn is non-negative, measurable, and Fn is in fact increases to mod F. So by the monotone convergence theorem, you have that integral over X mod Fn d mu will increase to integral over X mod F d mu, and that of course is finite in this case. Therefore, given any epsilon, there exists a capital N such that for all n greater or equal to capital N, you have integral over X mod F d mu minus integral over X Fn d mu is less than epsilon by 2. But since mod F minus Fn is non-negative because Fn increases, so this also implies that integral over E of mod F d mu minus integral over E Fn d mu is less than epsilon by 2 for all n greater or equal to capital N and for all E in S. Now F capital N is bounded, so there exists a delta positive by step 1 such that mu E less than delta implies that integral over Fn d mu over E is less than epsilon by 2, and therefore this implies that integral over E mod F d mu, which can now be written as integral over E mod F d mu minus integral over E Fn d mu plus integral over E Fn d mu F capital N, sorry. So this is less than epsilon by 2, this is also less than epsilon by 2, and therefore this is less than epsilon, and that proves this theorem. Okay, so remark, so if you define nu of E equals integral mod F d mu over E, then we already saw mod F is non-negative measurable function, therefore nu is a measure. So we say that nu is absolutely continuous with respect to mu. Okay, and we write nu in this form. Okay, so if mod f is integrable, then nu is absolutely in the continuous with respect to mu. And the Radon-Nikodym theorem, I have referred to this already, gives the converse. So for sigma finite measure spaces, nu absolutely continuous with this mu if and only if nu equals nu e equals integral f d mu over the for some f. Okay, so this is if and only if statement, and we will see this later, much later in this course. Okay, so every measure which is absolutely continuous with respect to a given measure will occur in this form, and f will be a non-negative, and if nu e is a finite measure, then this will be an integrable function, otherwise it's a general function. Okay, so our next aim is to, we have been discussing abstract Lebesgue integration, and our interest of course is about the Lebesgue measures in Rn or R, Rn, etc. So on R, for instance, you have two types of integration now. You have the Lebesgue integration coming from the Lebesgue measure, and you also have the classical Riemann integration. So we'd like to compare these two, and also that will help us how to compute the Lebesgue integral of some functions. We'll see that next.